I'm delighted to introduce Patrick Butlin, who is a research fellow at the Future of Humanity Institute at the University of Oxford. Patrick did his PhD on the topic of desire and the direction of fit. He's gone on to write several papers more in the Coxsai area, and he has a paper forthcoming in his Tempest, which is called Sharing Our Concepts with Machines. So today he's talking to us about machine learning functions and goals, which sounds like it's going to fit in beautifully with what we've been hearing so far. So Patrick, over to you.
Thanks very much, Anita. I also wanted to say thank you to all of the organisers for inviting me. It's a pleasure to have an opportunity to give a talk in person. It's been really fascinating to learn about Kathy Wilkes, and so I feel really delighted to be representing the University of Oxford here. So yes, I'm going to talk about machine learning functions and goals. So this is going to be a talk about agency, but I'm going to be emphasizing very different aspects of agency from those that Dennis talked about. So I don't think I'm going to say anything about levels, and I don't think I'm going to say anything about stochasticity. But I'm going to be talking about agency and about goals. Specifically, I'm going to argue for a connection between reinforcement learning and agency. Reinforcement learning is one form of machine learning, although it also seems to exist in animals, including humans. I'm going to suggest that reinforcement learning gives rise to goals, whereas supervised learning, which is another form of machine learning, gives rise to functions. Now, the distinction between goals and functions also exists in the biological context. It's natural to say that humans and other animals pursue goals, and that traits of biological organisms have functions. And I'm not going to have time to say very much about this, but basically how I think about the situation is that we should use the biological case to test my claim about goals and functions in machine learning. So I'm going to draw a distinction between goals and functions, then I'm going to revise it a little bit in light of some considerations about the biological case. My thought is that kind of what would prove me right about goals and functions would be if we found that the way I have of drawing this distinction also works well and fits well with biological ideas. A couple more preliminaries. First about agency. So the focus of this talk is going to be on minimal agency. That is the problem of distinguishing between agents and non-agents. So human agency is rich, it's flexible in many ways, it's perspective, we make plans, we think about the future in other ways. Human agency is also collaborative, it's massively, and separately, it's massively influenced by reflection on our own motives, our own characters, our own ways of making choices themselves. But I think that agency is possible in the absence of a lot of this. I think it's possible for there to be something which is recognizable as agency, which is much thinner than human agency. So that's why the problem of minimal agency arises. And as for what kind of account we should be looking for when we're looking for an account of minimal agency, well, I think that what it is to be an agent is to have capacities of the right kind and to be subject to norms of the right kind. And so what I'm going to be trying to do is say a little bit about what those capacities might be and what they're, and how we might characterize norms. And I think on a terminological note, I should also say something about how I'm going to use the term norms. So what I mean by norms is just non-arbitrary standards of correctness or of better or worse performance. So that's a very broad use of norms. It doesn't require anything like accountability, for instance, or anything like normative cognition, recognition that by the system that's subject to a norm, that is subject to a norm. So, for example, a photoreceptor cell on the retina operates correctly if it transduces light into fire in a certain way, and incorrectly if it doesn't do that. I think that's, well, at least according to the way that I'm going to use the term norm, that means that there's some non-arbitrary standard of correctness which applies to photoreceptor cells on the retina, and so they're subject to norms. Some people might think of this as, prefer to think of this as quasi-normativity and reserve the term norms for other contexts. That's just a terminological difference. So I want to start talking about minimal agency from Dretske's theory, which I think is a relatively promising account of what's required for minimal agency. So Dretske presents this view in various papers, which are all connected in different ways to the theory that he offers in this book, explaining behavior, reasons in the world of causes. And there are also various features of Dretske's theory which we don't need to pay too much attention to, because Dretske wasn't just concerned with agency, he was also concerned with content and with mental causation. But in any case, let me just give you a statement of the theory. So Dretske thinks that for a particular behavior of some type to be an action, it must be that that behavior is caused by an internal state of a certain type. The states of that type carry information about some feature of the environment. And then, crucially, that the behaving entity has learned to produce behaviors of this type when it's in internal states of this type, partly because those internal states carry information about the feature of the environment. So a much more intuitive and brief way to put that is that the entity must have learned to produce the behavior selectively in response to the environment being in certain states, or rather in response to its seeming, to put it in intentional terms, to the system that the environment is in those states. So here's one of Dretske's examples. A bird gets sick after eating a monarch butterfly. This causes it to avoid eating things which seem like monarch butterflies to it in the future. Dretske says that's a case where the bird has learned to produce this avoidance behavior selectively, and so that's an action. There are various objections to this theory. One of the most interesting ones is by Dennett, who objects that Dretske doesn't make it sufficiently clear why learning has to establish this relationship between features of the environment, internal states, and behaviors, rather than that relationship being established by evolution or by design. But that's not the objection that I'm going to focus on in this talk. Instead, what's going to concern me about Dretske's theory is that it doesn't seem to distinguish between behaviors which artificial systems produce as a result of supervised learning and behaviors which are produced as a result of reinforcement learning. Seems to me that the outputs of supervised learning systems are not instances of agency, because they're not produced in order to help bring about any further goal of the system. I'm going to talk lots more about that. So I'm going to be suggesting that if Dretske is right that learning is necessary for agency, then perhaps the ingredients for agency are something like learning and instrumentality, some kind of feature where behaviors are instrumental to the goal. So I'm not going to assume any knowledge of machine learning in this talk. We're going to start from the beginning. So here are Russell and Norvig in the standard artificial intelligence textbook defining supervised learning. What they say is that the task of supervised learning is this. Given a training set of n example input-output pairs, x1, y1, x2, y2, and so where each of these pairs was generated by an unknown function y equals f of x, discover a function h which approximates the true function f. Here's an example of a very famous supervised learning system. This is one of the systems which kicked off the last decade's exciting progress in artificial intelligence based on multi-layer artificial neural networks, known as deep neural networks. So this is a system called AlexNet. It's a deep convolutional network, and it's an image classifier. So what it does is, if you input an image to the system, which has to be in the right format and so on, then it will classify it according to one of 1,000 different categories which it's capable of using. And its training works like this. So at any particular step of the training, a random image is provided as an input to the system. The network outputs probabilities for each of the 1,000 labels. Then the system's provided with the correct label for the image that's just been input. And then there's a process in which the network weights are adjusted in a way which depends on the difference between the correct label and what the system thought was the correct output. So what's going on here is that in Russell and Norwig's definition, they wrote that the task of supervised learning is to find a function which approximates this true target function. What's going on here is that the network realizes a certain mathematical function in the way in which it takes inputs to outputs. And as the network gradually changes as a result of having its network weights adjusted, it gets to be a better and better estimate of the true function which is realized by the network. Okay, AlexNet seems to satisfy Dretske's account of agency. So it learns to produce outputs selectively. These outputs are caused by its internal states, and those states cause the outputs they do, partly because of the information that they carry about images. So you could, if you wanted to, look at some intermediate layer of this network, and you'd see that the patterns of activation at that layer would carry information about which image had been given as an input. And then you could also explain the output in terms of the pattern of activation at that middle layer. But more crucially, as a simple way to think about it, is just that this is a thing which learns to produce outputs selectively. But this thing, AlexNet, doesn't seem to be a good candidate for agency. It seems much more natural to me to say that AlexNet has a function. There's a certain output that it's supposed to produce for each kind of input, and as it improves, it gradually gets better at producing the right kinds of outputs for the right kinds of inputs. But these are just completely separate. There's nothing like interaction with the environment going on in AlexNet. It doesn't seem to be aiming to achieve anything. It doesn't look like a good candidate for agency. Okay, reinforcement learning in contrast. What Russell and Norwig say about reinforcement learning is that the task of reinforcement learning is to use observed rewards to learn an optimal policy for an environment. A policy is a function from states of the environment, which are inputs to the system, to actions which are the outputs of the system. And what makes a policy optimal is that it maximizes cumulative rewards. That's a crucial point which I'm going to keep emphasizing. What makes a policy optimal isn't that it maximizes the amount of reward that the agent receives immediately when it performs the action. Instead, what makes a policy optimal is that over an entire episode of interaction with the environment, the agent gets as much reward as possible. This diagram is from Sussan and Bartow's standard textbook on reinforcement learning. And of course, it's already labeled with words like agents and action and environment, because that's how reinforcement learning researchers think about these things. I mean, it's no coincidence that I'm going to be arguing that these things actually are agents or actually have crucial features of agency. But equally, we shouldn't just assume that the thing's an agent just because the computer scientists call it an agent. Okay, what's particularly noticeable about this is that we've got this feedback loop. So crucial difference from supervised learning is that what action the agent performs, so what output it produces, makes a difference to the next state that it's going to encounter. So let me just say that again. There's two differences, but these two are noticeable between supervised learning and reinforcement learning. One is that in supervised learning, the inputs are sampled randomly from the domain of the target function. So it's just, it gets one input after another as it's trained, the supervised learning system, like AlexNet. But those inputs are independent of each other and they're independent of the outputs that it produces. They're just sampled randomly. Whereas in reinforcement learning, have this feedback loop, the inputs depend on the previous inputs and depend on the system's outputs. And then another difference is that in supervised learning, the feedback which causes the system to be modified is the correct output for the input that it just received. Whereas in reinforcement learning, the feedback has got two parts. There's the reward signal, and then there's also the next input, the new state, which the system finds itself in. Here's an example of a reinforcement learning system. I'm going to describe this in a little bit of detail, a little bit more detail than I did AlexNet, but this detail is somewhat important. So this is a system which we can call DQN for Deep Q Network, and this is one of the breakthrough pieces of research which was one of the first high-profile ones produced by DeepMind, the major AI lab in London. So DQN is a neural network which learns to play Atari games. It achieved better than human level performance on a wide range of Atari games, although it has to be trained on each game separately. Can't learn to play them all at once.
So what's Q for?
It's just Q, it doesn't stand for anything. Yeah. So I'm going to be talking about the Q function, but I mean, I guess there's a reason why they chose Q, but it doesn't matter.
So it's not quantum.
No, it's not quantum. Okay, so as I described in the case of AlexNet, when you've got one of these artificial neural networks, what it does is realize a mathematical function. And the function which is realized by the neural network in the case of DQN is the action value function, Q, which is a two-place function. It's a function from state action pairs to numbers, numerical values. And Q gives the cumulative reward that can be expected after performing action A in state S. So what's crucial about that is that the Q function for a particular action doesn't give you the reward that you're going to receive immediately after performing that action. Instead, it gives you the total, or possibly it's the discounted total of the reward which you're going to receive in the long term after performing that action. Not just immediately, but after the subsequent actions which you're going to perform as well. So it measures how good an action is in some more substantial way, and a way which is actually more relevant to good behavior, given how optimal behavior is defined. So, as I said earlier, optimal behavior is behavior which maximizes reward over whole episodes of interaction. So the Q function is crucial to telling you what you want to do if you want to try and behave optimally. Okay, how does Q learning work? Well, I'm afraid I have to go through this. I'm going to give you an example on the next slide, which I hope will make it a little bit clearer. Like with the supervised learning, what we're going to do is gradually improve the neural network by making small changes at each step based on the difference between what the network is currently like and what the feedback indicates about what it should be like. So specifically, estimated Q values are updated in the direction of the temporal difference error, which is this expression here. And in this expression, R is the reward that's received after performing an action. This expression over here, QSA, that's the system's current estimate of the value of the action that it's just performed. And this one, gamma QS-A-, is the system's current discounted current estimate of the value of the best action which is available from the new state that it's just got to. So S' is the new state that it's just got to by performing the action. So to cut to the chase, the implication of this formula is that if you just performed action A, your estimate of the value of that action is going to go up if action A either leads to lots of reward, or it leads you to a new state which you currently expect is very valuable. Now, the reason why that's useful can be illustrated by an example like this. Unfortunately, you can't see everything because of the Zoom, but oops. So this box over here says S4 in it. So these S's are states of the environment that the system can encounter, and the A's are actions that take them from one state to another. And let's suppose that S4 is a really good state to be in, S2 is pretty mediocre, and S3 is better than S2, but not as good as S4. So suppose, for instance, that in S2 you get nothing, in S3 you get some chocolate, and in S4 you get a house in the south of France, like Tennis's house. Then obviously what we want the system to learn to do is to take action A2 when it finds itself in S1, because A2 is actually much better than A3. If you take A2, you get to S2, and from S2, S4 is accessible. And the deep Q network can learn to go from S1 to S2. So how this works is that, well, so first it's got to have experience of going from S2 to S4. If it's had experience of that, then it's going to receive a high reward. And that means it's going to represent this action A4 as having a high Q value. It's being a good action to perform. Now, if the system later goes from S1 to S2, maybe it's done that before, maybe it hasn't, doesn't matter, but later goes from S1 to S2, then it's going to learn to put a high value on A2, even though it doesn't get very much reward at S2. And that's because its current estimate of the value of being in S2 is a high one. So what we see is that over repeated interactions with the environment, we get this kind of propagation backwards of representations of value. So first, it just thinks it's great to get here. Then, because of that, it thinks it's great to get here. And then because of that, it thinks it's great to get here and perform this action. Okay, hopefully that makes things clear. So I've already said this, but key feature of reinforcement learning is that, in general, maximizing immediate rewards is not the optimal policy. To perform well, the agent must exploit the fact that its actions influence the next state by working to reach states from which variables are available. And as I've just explained, Q-learning does this. There's lots of other reinforcement learning algorithms as well, and all the good ones, all the ones which will be taken seriously, would also do this. So a change of gear now, I'm going to talk about functions and goals. So people mean slightly different things by selection, but I'm going to say that selection is any process in which there's either differential reproduction in a population, or alternatively, persistence or modification of some entity according to some criterion, which can cause cumulative adaptation. So the thought is just like the system goes along for a while, then there's some kind of filter which causes it to persist or be modified, or causes differential reproduction. And then it's kind of meets this filter repeatedly, so certain features come to persist in the system, ones which are good for passing through the filter. And as I said in my question today, it's widely believed that selective processes can give rise to functions. So standard example is that the heart's function is to pump the blood. This is so because pumping blood is the effect of the heart's activity that causes it to be preserved in the course of natural selection. This seems to ground teleological explanations, like the heart exists to pump the blood, and it also seems to ground normative claims, such as the heart fails when it stops beating. Now, in that context, I think it's right to say that norms arise in the course of machine learning. So both supervised learning and reinforcement learning are selective processes which cause systems that use them to become subject to norms. So in supervised learning, well, during training, a supervised learning system like AlexNet, if it produces the right output, then it's left unchanged. If it produces the wrong output, then it's modified in a way which makes the right output more likely. And that goes on repeatedly until it gets better and better at producing the right output, that is, doing the thing which leaves it unchanged. So its network rates are selected by this process for a certain set of input-output dispositions. I'm going to skip that slide because I know I don't have enough time. In reinforcement learning, rewards lead to changes which make actions more likely. Negative rewards lead to changes which make actions less likely. Again, there's this process of gradual modification according to that standard. So again, it looks like that selection process is operating. Combinations of network weights in something like DQN are selected for causing high value actions. So my thought is that if agency is something to do with being subject to norms of the right kind, then we should wonder, is there something different about these two processes of selection, the one that takes place in supervised learning and the one that takes place in reinforcement learning, or something different about the norms that they give rise to, which could justify my intuition, and clearly the intuition of other computers, well, the intuition of computer scientists, of whom I'm not one, that reinforcement learning has got something to do with agency, supervised learning doesn't. An insignificant difference first it's natural to say of AlexNet's outputs that they're correct or incorrect. It either gets the right label or it doesn't. Whereas with DQN, looks like the standard that we're inclined to apply isn't a correctness or incorrectness standard. Instead, it's a better or worse standard. Actions can be more or less conducive to maximizing reward. But I think that's not the difference that we're looking for. Supervised learning can also give rise to better or worse norms. For instance, in the case of GPT-3 does better or worse at selecting the most probable next word. So what's the significant difference between reinforcement learning and supervised learning? Well, another difference is that what makes the reinforcement learning system's actions better or worse is how they contribute to its performance over whole episodes. And that's not true in the case of supervised learning. There are no whole episodes. Each instance of classifying an image is independent from the others. It seems like the norms that apply to individual outputs of reinforcement learning systems are derived from prior norms over episodes. We start with this goal to maximize reward, and then what makes the system do better or worse on an individual occasion is how well its output contributes to that. Whereas with supervised learning, the like overarching purpose of the thing is just classify images correctly. Well, that's already a description of what it's supposed to be doing on individual occasions as well. This isn't just an interpretative gloss on the Q function, the function that the deep Q network learns. Instead, there's some grounds to it, I think. It's grounded by the sensitivity of the learning process to how actions contribute to the reward. So my initial proposal about this difference between these two forms of machine learning, and the reason I'm calling it an initial proposal is because I'm about to revise it, is that for a system to have a goal is for it to be subject to a norm of good performance, which applies to its interaction with the environment, which is prior to norms applying to individual outputs. I think systems of this kind with goals exploit the effects of their outputs on the environment to perform well in extended interactions. And I'm suggesting here that being an agent involves having a goal, although there's a question mark there because haven't said anything about what kind of involvement this is, whether this is a necessary or sufficient condition. Okay, so like I said at the beginning, in order to test this proposal, what I think we need to do is consider cases from biology. I think the proposal would be in trouble if either there were kind of paradigm biological non-agents, like organs like the heart, which had goals in the sense in which I have defined goals. That would make it seem like this wasn't the right way to understand what it is. And I think the proposal would also be in trouble if there were paradigm biological agents which didn't have goals in the sense in which I've defined goals. I'm going to focus on the first of those two, both because I've got limited time and also because I haven't thought very carefully about the second one yet. Okay. So we want some cases of non-agents in biology, and perhaps there are none, but let's assume for the sake of argument that neither flowers nor plants are agents. The reason I put diffusively there about plants is that, you know, we've started learning a little bit about what's described as plant cognition recently. We could learn more. I'm open to the possibility that I could be convinced that plants are in some sense agents. Anyway, that's an aside. So, thinking about flowers first. Do flowers have goals in the sense that I've defined? Well, I didn't choose flowers randomly. Flowers are interesting because it looks like they do exploit feedback from the environment. They're using to do things in order to cause the state of the environment to change, in order that will then like allow them to do future things. So what they do is they attract pollinators, and then the pollinators fertilize the flowers, and then that makes it possible for them to produce and scatter fertile seed. So you might say, well, here's an example of something where we've got this prior norm, the norm of producing fertile seed, and then a subnorm arises from it, which is to release some volatile compounds in order to attract pollinators. And so flowers are pursuing goals according to my standards. Well, I don't think that's quite right. So, for sure, it's certainly true that, maybe that's too strong. It seems true that in order to explain why flowers smell nice, why they release these volatile compounds, we need to say something about what further function they're going to perform by doing so. So we need to ascribe to them the function to produce fertile seed. So there's some kind of explanatory priority of the function to produce fertile seed over the functions of these volatile compounds. But this case seems pretty disanalogous from the case that we saw in reinforcement learning, because in reinforcement learning, the prior goal to maximize reward is driving selection. Whereas selection isn't driven by the production or otherwise of fertile seed. Instead, selection in flowering plants is driven by the production of offspring, which involves more than just producing fertile seeds. So it seems like both seed producing and scent producing are selected for their contributions to fitness. So there's some sense in which they're actually on a par of these two functions, even though one's explanatorily prior to the other. I'm not too confident about that, but I'm not sure that it's the main issue anyway. Here's what I think might be a bigger issue. So, you might think, I'm not sure that this is a common view, but I don't know enough about biology to say for sure. You might think that the parts and behaviors of whole organisms are subject to norms which are derived from a norm to maximize fitness. Now, if that's right, then again, it looks like the same kind of objection point of view is possible. We've got this prior norm, other norms that are derived from it. Now, one thing that I might potentially say in response to this objection is, well, if we're focusing on plants, plants arguably don't produce whole organism behaviors. Maybe everything that plants do can be attributed to specific parts of the plant. If that's true, I'm not confident that it is true, then you might say that this is different from the case of reinforcement learning, in which it's outputs of the whole system which yield reward, which are instrumental to achieving the prior goal. So one possible view is that what it is for a biological system to act, to be an agent, is to produce whole organism behavior. And Tyler Birch actually develops and defends that view in a paper from 2009. But I'm not a fan of the view, and the reason is I think that the notion of whole organism behavior is a bit shaky. I'm not sure how to distinguish behaviors that are produced by whole organisms from behaviors which are just produced by plants. In any case, as I hope this talk illustrates, I'd like a more abstract account of agency which applies equally well to the machine case as to the biological case. So instead, I want to just think a little bit more slowly about whole organisms, about the idea of maximizing fitness, and try to relate that to the ideas about reinforcement learning and supervised learning that I was presenting earlier. So I suggested when I was talking about supervised learning and reinforcement learning that something like the criterion for selection itself becomes a norm which the system is subject to. So in the case of reinforcement learning, features are selected for their contribution to maximizing cumulative reward, and I said in virtue of that, the whole thing, the whole reinforcement learner is subject to a norm which says maximize reward. Similarly, with supervised learning, the criterion for selection is something like closeness of its performance to the system's performance to the target function. And I said that gives rise to function for whole supervised learning systems, which is to approximate the target function as closely as possible. Now, with natural selection, the criterion for selection is something like fitness. That's being deliberately vague. I don't know exactly how we should characterize it. But I don't think it matters for our purposes. So it seems like by parity of reasoning from the reinforcement learning and supervised learning cases, we should say that organisms are subject to a norm to maximize fitness. But the fact that I was just drawing that three-way analogy between both forms of machine learning and natural selection is already a suggestion that natural selection isn't going to be a problem for me because, after all, there's a difference between reinforcement learning and supervised learning. So maybe natural selection is just like supervised learning. So I want to suggest that there's a disanalogy between reinforcement learning on one hand and the other two things on the other hand. Yeah. That's fine. In natural selection and in supervised learning, selection is driven only by the extent to which the criterion selection is met immediately. It's like in the supervised learning case, is this the correct output or not for the input that's just been provided? That's what determines what changes take place in the system, what it's like in the next stage. Similarly, in natural selection, do you manage to produce lots of viable offspring or not? Well, no, sorry, I should say, do you manage to produce lots of offspring or not? If you do, then your traits are going to be prevalent in the next generation. If you don't, then your traits are not going to be prevalent in the next generation. But in reinforcement learning, it's not as simple as that. The system stores information which it's previously learned about the conduciveness of states of the environment to success. And they then that information then influences modification of the system. It's not just how much reward it gets that influences what happens, it's also what it expects about the value of the new state that it observes the environment moving into. So in reinforcement learning, the process of selection itself works in a way that takes into account the system's effects on the environment and exploits those effects on the environment for greater cumulative success. Okay, just to wrap up now, what have we learned from testing my proposal by thinking about natural selection? Well, it seems like in my initial proposal, I was wrong to talk about prior norms. That doesn't clearly distinguish reinforcement learning from either the biological case or supervised learning. Because in both of those cases, we've got a norm which applies to the whole system, and then we can talk about functions of particular parts or traits, features of the system, which are subordinate to that prior norm. That was the wrong way to talk about it. Instead, the crucial difference is that in reinforcement learning, selection is sensitive to the effects of actions on the environment as well as on immediate chaos. So perhaps what it is for a system to have a goal is for its activities to be subject to a regime of selection for this particular challenge. So going back to Dretske, what I want to suggest is that if we accept Dretske's view that learning is necessary for agency, then maybe we should add a further condition to his account, call it something like instrumentality. For something to be an agent, for it to be performing actions, must be that those actions are performed because their effects on the environment make future rewards possible, or they contribute to good performance over an episode of interaction. I think actually, and this goes back to Dennis' criticism that this feature of a system can exist without learning. But I think perhaps what my argument shows is that quite a specific form of learning is required to produce it. And that's all. Thanks very much.